guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept still in one of the application of a cross product of vectors, and this basically is going to entail another new idea that of course we talked apart from the two concepts that we had talked about, the vectors of a cross product, which was the idea of a orthogonal or perpendicular, the vectors which are perpendicular, which basically we referred to as the right hand system. So in our discussion for today, we're going to see that there's an identity that we're going to call the Lagrange identity, which we of course mentioned in our last video and said that we are going to have a discussion for it in this specific video. So for today, we're going to see also another application of the cross product of vectors, and basically which is going to deal with the Lagrange's identity or theorem. So without further ado, thank you and welcome. So as I've said, we had already mentioned this particular concept about the Lagrange's identity, but we said that we will just reserve this one for this specific discussion because it's one of the wider applications of the cross product of vectors that we had mentioned. And of course, in trying to discuss, or maybe basically trying to lay a basis for that, we had said that there is the concept of orthogonal vectors that we had discussed, whereby we gave the equations and said that if u and v are vectors in the three-dimensional space, then therefore A, we said that the cross between the dot product between the u and the cross of uv is going to give us 0. And therefore we concluded that this component of this particular expression for u, v, or this cross is orthogonal to u. And basically we said that if we take a different approach for v, u, v, it's basically also is equals to 0. And we said therefore u, v is orthogonal to v. And this gave us a concept of the right hand system that we normally talk in trying to represent quantities either in physics or maybe mathematics, like in trying to find the magnetic fields and other quantities, of course, which imply the application of vectors, like the magnetic field that I've talked about. This right hand system is very much applicable, and so therefore we say that this is a vector AB, and they're forming that specific angle. We can call this one the plane. This specific area is the plane of a vector AB, and if there's a vector that is perpendicular, which we can be able to refer to as the n hat, which represents the norm, a vector which is a normal or maybe perpendicular to this plane of AB, then this vector is going to form, the combination of this is going to form what we call a unity vector for A. So this is going to form A cross B, and this is going to form a system that we call a right hand system. That of course we have said we can use to define in some quantities like magnetic fields, etc., that use the right hand system, of course, in its application. So apart from this, there's a third, apart from A and B, there's a third concept that we had mentioned, of course, which is a point of discussion for today, which was the Lagrange's identity. That was point number C. So which we had written as, so C was u cross v squared is equals u v squared minus u dot v squared. So this one we refer to it as the this identity. So in some areas we might be using or referring to this as Lagrange's theorem, and it's going to form a basis for discussion for today. Now, from the already discussions that we have had in some of our videos, we said that for us to represent U in a three-dimensional space, we can say it's a U1, U2, U3, and therefore for V it's going to be V1, V2, V3. And if you try to have a cross product between UV, this is going to give us U2, V3 minus U3, V2. That is for the I component. And then we're going to have, I'll be forced to do away with this. So then we're going to have a U3, V1 minus U1, V3. And then for the K component, we're going to have U1, V2 minus U2, V1. So the cross product of this is going to give us that one. And then we said that U can be represented like this. Now from the concept of the orthogonal vectors that we have talked about, we can be able to represent the U dot U cross V using these specific components that we've talked about for U1, U2, U3 dot the whole of this. So it's U2 V3 minus U3 V2, U3 V1 minus U1 V3, and then U1 V2 minus U2 V1, like that. So in this case, this product is going to give us 0. Now suppose we have a cross for, just do away with this. Now suppose we have a cross for UV. So U cross V, and then we're going to find, we said those signs represent the norm. We're going to find the norm for that specific vector. So this therefore can be represented as a norm for the whole of that component for U2 V3 minus U3 V2, and then U3 V1 minus U1 V3, U1 V2 minus U2 V1. And then we're going to find the norm for that. So in us finding the norm for that, we'll find that this is going to be, of course, U2 V3 minus U3 V2 squared plus U3 V1 minus U1 V3 squared plus U1 V2 minus U2 V1 squared. So that is going to represent the norm for this specific vector. Now suppose we square that norm and have this specific identity. This is going to give us, no, because of space, it's going to give us the product for this specific identity that we have already mentioned on the board, bearing in mind that of course I'm just going to limit this one at this point because of space, but suppose we square this, is going to give us this specific section of that Lagrange identity that you have mentioned. But note that we had already discussed about the concept of the cross of U dot V squared being given as U or UV, U dot V being given as U1 V1 plus U2 V2 plus U3 V3 for those specific vectors that we have listed in a three-dimensional space for U and V respectively. So suppose we are to square this, then we are going to have this also the square of this specific point. So that implies that this is going to give us the second part of this specific identity. So we also have an application for this Lagrange's identity or theorem that I've talked about, which we're going to see also being applied like the cross product of vectors that I talked in one of our videos concerning the area of a triangle, given the the coordinates for its vertices, and therefore we can be able to apply that. So we're going to see how we can be able to use the Lagrange's identity in order to find the area of maybe a triangle, given those specific concepts that we have already discussed. So I'm just going to do away with this. Now, if you look at this particular case, we said that if theta is the angle, I'm just going to use those signs between two vectors in a three-dimensional space u and v, then we say that the cross product u dot v can be given as the norm of u, the norm of v, and then cosine of theta, which is the angle between those two vectors. Now, if we try to square this particular formula for finding the dot product of those two vectors, then we're going to have u dot v squared being given as the norm of u squared, the norm of v squared, cosine squared of theta. So in this, we have already said that from the Lagrange's identity, we have said that the norm of u cross v squared is given as the norm of u squared and then the square of the norm of v minus the square of the dot product of u dot v. So if we try to look at the relationship between these two specific identities that we have given, this first one for finding the dot product of two vectors can be able to be represented as this. So therefore we can just do a substitution for that and try to find another way in which we can be able to represent the Lagrange's theorem, Lagrange's identity, whereby this is the square of u, the cross of uv is going to give us the norm of u, the norm of v squared, and then minus this. Now we do a substitution for this, which is going to give us minus the norm of u squared, the norm of v squared, and then the cosine squared of theta. So that's a second representation. So for our case, we've just done a substitution for that. Now basically trying to rearrange this specific side of the equation. Therefore, we're going to have this Lagrange's identity represented as the norm of u squared and then the norm of v squared into 1 minus the cosine squared of theta. But from trigonometric identity, we have learned that this specific is the sine squared theta plus the cosine squared of theta can be given as 1. So doing a rearrangement of that, this is going to give us the sine of theta. So basically this is the sine squared of theta. So we can be able to do a representation for that and then find the Lagrange's theorem is going to the norm of u squared, norm of v squared, the sine squared of theta. Now remember, this is of course a cross square of a cross product that we have already discussed. So basically it's going to give us this is the uv squared is going to give us that specific expression. And figuratively, if we try to represent this particular formula that we have written using the trigonometric identities or the Pythagoras theorem, I'm just going to use a figure to illustrate how we can be able to represent this specific formula. So therefore, suppose we have two vectors that we have talked about, whereby this is a vector u, vector v, and then they are just coinciding at this specific angle theta. We can be able to form a right triangle at that specific point. Now the representation of those two vectors, as I said, we can form an imaginary figure of a parallelogram, which we can be able to represent as such. So bearing in mind that, of course, this is for vector u, as I said, we can be able to represent those one as vector u and v. Now the area of, as we said, we can find a cross product in order to find the area of a regular figure that we have discussed in our previous video for a parallelogram. So therefore, we can be able to find the area of this particular parallelogram by trying to define or use the concept of trigonometry that we discussed. Now in this case, for the case of this one, for our reminder, we can say the sine of theta from the three identities that we talked about. The sine of theta is represented as opposite h over the hypotenuse, which we can give us the norm of v. Therefore, h can be represented as the norm of v, the sine of theta. I'm trying to create a connection between those specific points. So in this case, we're going to see that this area of a parallelogram can be given as the cross product between this and this vector. So therefore, we can be able to say, or we can conclude that u cross v from this specific point is given as the norm of u, the norm of v, the sine of theta. But if you try to look at this section of the formula together with what we have already found at this specific point, then it will be correct for us to conclude that this section of the formula represents the height. So this basically is the height, which is going to be represented as h. Therefore, that formula is going to be the u cross v. It's going to be the norm of u and then times height. So the area for this specific parallelogram is going to be the norm of u, which is base times height, basically, when we try to find the area of a parallelogram. So in trying to find the relationship that exists between this trigonometric identity, the Lagrange's theorem, and coming up with this specific formula, we can be able to find the area of a regular figure, like the one that we have already illustrated on the board. So this is one of the application of our Lagrange's theorem or Lagrange's identity that we have already listed. And as we move ahead, we can be able to see a combination of ideas from the trigonometry, the Lagrange's theorem, the concept of orthogonal vectors, in trying to find areas of specific figures. So this will assist us in trying to solve some of the problems that we may come across by trying to match or maybe apply the concepts that we have learned together to complement maybe the one that we have already discussed. So always try to remember that apart from the concept that we have discussed about of orthogonal figures, the concept of trigonometry and the Lagrange's theorem are going to be of basic use in some of our other videos that we're going to discuss, but we are also going to remind ourselves in case we come across one that this represents the Lagrange's theorem or identity, or maybe this is from the cross product. And I'm going to put a link of the list of videos that we have discussed on the same, so that in any case we need to find out or reference, it will be easier for us. So that is it for today, guys. I hope these concepts of Lagrange's theorem and the other applications that you have already try to complement or maybe try to merge together to come up with this concept have been understood, and we will apply them appropriately in case we come across them. So that is it for today. Bye guys. God bless.